Alright, hello, my name is Thomas Trifu, and this is my Project 1 for Fluid Mechanics. So to start off, we're just going to create a Fluent system. I'm going to click on Geometry, go over here, swap it to 2D, and then right-click and enter with Design Modeler. This might take a second to load. Alright, here we go, we're in Design Modeler. I'm going to click into the XY plane, orient my graph, go to Sketching, Rectangle, and then give it some dimensions. I'm going to give it a vertical dimension and a horizontal dimension. I'm going to swap my units to millimeter and then write these in. The horizontal dimension is 750 millimeters, the vertical is 5 millimeters. You can see it is 150 times longer than it is tall. So now I'm going to go to Modeling, going to select it, then go to Concept, Surfaces from Sketches, Apply, Generate. And now we've got our geometry. Easy enough. Now let's make a mesh. Alright, here we are in meshing. First thing I'm going to do is name all my sides. I'm going to name this the upper wall, the one below it the lower wall, of course. I just zoomed by accident. Lower wall. And then I'm going to have the inlet. And the outlet. Make sure they're all there. Good. Alright, and next thing I'm going to do is click on Mesh, right-click, Insert, Sizing, and then I'm going to select the inlet and the outlet. Apply, change the type to number of divisions. I'm going to give it 50 divisions. Do not capture curvature and hard behavior. Everything else is fine. Generate that. Should be pretty quick, only 50 divisions. Very good. Click back into Mesh, Insert, Sizing. Now I'm going to click the top and bottom. Apply. Going to do number of divisions again, but this time 2,500 divisions. This one's going to take quite a bit longer. I'm going to swap this to hard and capture curvature to no, and generate. Okay, that mesh is now done. I'm going to click back into mesh one last time, right click, insert, face meshing. I'm going to click this face, apply, all the defaults are good, generate. That was done pretty quick. Just to check, click back into our mesh and scroll in. I want to see little rectangles. Very good. Looks good. Okay, and with that we can go back here. We can update the mesh. And then I'm going to duplicate this system twice, because we've got 3 different cases to go through, and I'd rather just have them all separate. Make my life easier. Okay, and now on this one I'm going to click into Setup, check Double Precision, open that. I'm also going to close out of the Design Modeler geometry and the meshing, just because I won't need those anymore. Okay, so here we are in the setup. This is where most of the actual interesting stuff happens. So the first thing I'm going to do once it loads in is I'm going to go to Models, and I'm going to make sure our flow is viscous laminar. That's what we want. Right now it's viscous SSTK omega. Swap it to laminar, click OK. Then I'm going to go to Results, Residuals, and make all my residuals a little bit lower, 10 to the negative 6. Alright, then Materials, Fluid, double click on Air. I'm going to keep it as air, but I am going to change its properties. I'm going to give it a density of 1 kilogram per cubic meter, and a viscosity of 10 to the minus 4 kilograms per meter second. Then I'm going to go to not cell zone, boundary conditions, inlet, double click velocity inlet. And the first thing we're making is the Poiseuille. Yeah, is that how you pronounce it? I don't even know how to pronounce it. I think it's Poiseuille. But we're going to make that flow case with a velocity of 20 meters per second. Apply that, close it. Just going to make sure the outlet prevents reverse flow. We don't want flow coming back into our system. And then the lower and upper walls by default are stationary, which is exactly what we want. Just going to make sure of that here. We don't want the walls to move yet. We'll want them to move for the Couette flow and the hybrid flow, but not this one. Then I'm going to click into reference values. I'm going to select inlet as the place it computes from. Check all these values. They all look good. Reference zone surface body. Go to initialization, click into it, and then right-click initialize. This might take a minute. Okay, the initialization process is done. I'm going to click into run calculation and then double-click it. I'm going to change the number of iterations to 500. It's a bit overkill, but yeah, you know what? I'm going to switch it to 300 and then calculate. It never usually reaches 500 iterations. I mean, usually it reaches conversions by like 150 at most. Okay, the calculation is now complete. I'm going to click OK. And then vectors, new. I'm just going to add a vector field so we can get a first look at what's going on. Select the main surface, the interior surface body, and then close that. And then here we go. This is what it looks like. Towards the undeveloped part, you can see it initially starts at pretty much a uniform velocity, and then as it goes on, it becomes more and more parabolic. You can see the shadows of these arrows in a parabolic shape until by this point it's pretty much fully developed. And yeah, this is Poiseuille flow. Okay, I'm going to go back to here, click into results so we can get a better look at things. This might also take a second to load. Oh, not that long. Alright, I'm going to orient my, my view this way, and I'm going to add some lines. The first line is just going to be in the developing region. This one's just because the midline and the end line are usually pretty close together, so it's hard to really see much difference. There's a little bit, but there's really not much. I made this one 50 millimeters in. It's just as tall as this thing is, and I gave it 101 samples. The midline, I'm going to put it right at the middle, 375 millimeters. And just as tall as the object is. Gonna give it 101 samples, apply, and then the end line. This one I'm gonna put just before the end to make sure there's no continuity errors. I haven't really seen anything go wrong if you put it right at the end, but I've heard it does. So give it 101 samples again. Alright, and then we've got all three of these lines, and they all look good. Alright, next I'm going to add a contour map. And this contour map is going to have 101 contours. It's going to measure the velocity u. It's going to measure it over the entire symmetry 1, which is the interior. And it's going to look something like this, if it loads. There we go. Alright, I'm going to just adjust this legend because it's quite ugly. Switch it to horizontal and fixed. And now it's up there. And here's our Poiseuille flow. It looks very similar to the vector field that we just looked at because it's pretty much the same thing. It's still color-coded. The only difference is now you're not dealing with vectors, you're just dealing with colors. But once again, at the beginning, it's pretty much uniform velocity. And then as it goes on, it becomes more and more quadratic and gets that nice Poiseuille flow look to it. Okay, so I forgot to show the chart before for the Poiseuille flow, so I'm going to go to Insert Chart, and then rename this to Poiseuille flow data series. We're going to add the developing line, or developing region, the midline, and the end line. X-axis is going to measure velocity u, y-axis is just going to measure y. Hit apply. Here we go. Okay. So the developing line, the red one, isn't quite a parabola yet. It's getting there. As it develops, the peak starts to pop out more and more, and it gets dragged this way until it eventually reaches the end line, which is a normal parabola. You can see the midline just barely at the tip area. At the vertex, you can see just a thin blue line to the left of the green one. And that's because the midline is just barely lagging the end line. And it's just the end result of this developing line in red here. Alright, with that said, we're just going to exit out of both of these. Sure, we could save. Exit out of both of these, and then reopen. Now in our second iteration, I'm going to double-click Setup, check double precision, and let's get started on the Couette flow. So the main changes are just going to be, we're going to have a moving upper wall here. That's going to be the main change. There is something interesting that I really should explain myself when I do it, which has to do with the inlet. And I will discuss that more when I get there, but first let's just redo what we already did. Change that, go to results, residuals, make this the same. Okay. Then materials, fluid, oh, okay. Air, 1 and 10 to the negative 4, change/create. Alright, boundary conditions, inlet. I see a lot of people, especially at least in the tutorials that I watched that were provided, and also just on YouTube, that they swap this to a pressure inlet. And I don't think that's a good idea, because when you do that, you leave the system to determine for itself what the initial velocity is going to be. And it's better if you just define that for them, so they don't have to figure it out. Because if they do try to figure it out themselves, they're going to get it wrong. And when they get it wrong, they try to enforce a constant volumetric flow rate, and they're going to enforce it based off the wrong initial velocity profile. So instead, I'm going to just give it to them on my own. I'm going to give it a velocity magnitude of 10 meters per second, which will make sense in just a second. I'm then going to go to the outlet, going to check reverse flow, or prevent reverse flow. And then I'm going to go to the upper wall. The lower wall, once again, is stationary by default. That's what we want. And this upper one is going to be moving with a speed of 20 meters per second. Note that the speed I put in for the inlet is exactly half of this. It's the average speed in the fully developed Couette flow, where it's linear. The average speed is 10 meters per second, and so the volumetric flow rate is based on that. We want to make sure the volumetric flow rate at the beginning matches that, so I inputted 10 meters per second right here. Okay, down to reference values. Let's click into this. Compute from inlet. This all looks good. Reference zone surface body. Then click into initialization. Right click initialize. This might take a minute. Alright, initialization is complete. Gonna click into run calculation, then double click. Change the number of iterations. This one's a bit more stiff. I'm gonna put this at like 400 and then hit calculate. Alright, this calculation is now complete. It was a whole lot less stiff than I thought it would be. I remember it being taking much more time and much more iterations to get to convergence. Anyway, let's view the vectors just to get a basic idea. And there we go. That's exactly what I wanted to see. Note that this is more yellow-ish of an initial velocity profile than you might see from other people. And that's because we set a specific velocity right smack dab in between the minimum and maximum. If we were to let Ansys take control and select it themselves, they would select a velocity that's around here. So for us, in our case, it would be like 8.2 or 7.8 around there, which would totally mess up the volume flow rate, and then that would just mess up calculations. But either way, this looks good. This is exactly what I was hoping for. And then you get on. By this point, it's pretty much fully developed, and you can see a nice linear pattern right here. But to see it better, we go to results, and then we do basically the same thing we did before. I'm going to reorient this. Then I'm going to create my lines again, developing region. This is going to be 50 millimeters in, 101 samples, very good. Then midline is going to be 375 millimeters in with 101 samples. And then the end line. Okay, and then I'm going to add a contour map with 101 contours. I'm going to switch this to velocity U, location to symmetry 1, and apply. And here we go. It looks pretty much the same as the vector map from before. Oh, so we've got, once again, starting out at around 10 meters per second, and then it slowly morphs into your linear Couette flow. Oops, keep doing that. And now you've got pretty much a linear Couette flow. Very nice rainbow. And then we're going to go to chart. Going to insert chart. The title is going to be Couette flow. And I'm going to add all of my lines. Developing, midline, and end line. Going to make the x value the u velocity, and the y value y, and hit apply. And here we go. This is a perfectly linear Couette flow. That's the end line, the green. The midline is pretty much right on top of it. You can see a little bit of it bulging out this way underneath the green line, and you can see a little bit bulging out this way above the green line, kind of mimicking how it is before, but just if you take these humps and you shrink them in, when you're right about to hit the end line, that's what the midline is doing. This kind of looks like a string that you're holding in an S shape, and then you snap it taut. That's how this develops. Alright, now we're back at the workbench. I'm now going to go to my third setup. Going to check double precision, get started. And now we're going to do the hybrid. This is going to be the mix of Poiseuille and Couette flow. And this should be pretty straightforward. It's very similar to the previous one, which was just Couette. It's going to be pretty much the exact same setup, except I'm going to change one of the values. So going to go here, change this to laminar, hit OK, go to results, residuals, doing this all over again, 1e to the negative 6 for all of these. Materials, fluid, air, Density of 1 kilogram per cubic meter, viscosity of 10 to the negative 4 kilograms per meter second. Boundary conditions, inlet. The velocity here I want to make 20 meters per second. That's the amount that I decided. So I'm going to apply that. Go to the outlet, make sure there is no reverse flow. Very nice. The lower wall, going to keep stationary, which is what it's set to by default. But this upper wall, I'm going to set it moving at 20 meters per second in the right direction. So the wall is moving 20 meters per second. The fluid's initially moving 20 meters per second. Let's see what happens. So reference values, let's make sure these are computed from the inlet. And then the reference zone is the surface body. Initialization, click into it, and then right-click for initialize. Alright, the hybrid initialization is now done. Going to click into run calculation, then double-click it. Then I'm going to type, how many iterations here? I think 300 should be good again. I rarely see it go above that. So I'm going to hit calculate and then wait again. Okay, this calculation is now complete. Going to now just set up a little vector map just to get a first look and examine the vectors, the velocity vectors. Scroll in, and there you go. Initially, it's pretty much, except for right here, a uniform velocity. The only reason it changes here is to match the no slip conditions set by this stationary plate. But then, as it evolves, it becomes a bit more parabolic in nature, but it's not a symmetric parabola, which is what we want. We don't want it to be a symmetric parabola. We want it to be offset a bit, which is pretty much what this is doing. With that said, we can now go to results. We can click into it. Okay, here we go. For the last time, we're going to create 3 lines. I'm just going to name this developing. Same exact features as before. Midline. And an end line. Okay, and a contour map to go with it. This is going to have 101 contours, velocity u, location is going to be this first symmetry, and hit apply. Alright, here we go. Gonna adjust this legend so that's a little neater. It's over here now. We can scroll in, and it's pretty much the same thing that we just saw again. We can see it originally is pretty much uniform, and then slowly it starts to fan out, and the redness deepens. It gathers on this top piece, which is once again what we expected from a mixed flow like this. So now we're going to go to create chart. We're going to name it hybrid flow. Go to the data series. We're going to add our 3 again, developing, midline, and end line. Our x-axis is going to be our u velocity, and our y-axis is going to be y. Hit apply, and there we go. The red line is developing, so you can see it's still quite flat here. It's still recovering from the uniformity at first, but it's sort of getting its form, and then by the midline, it's pretty much fully developed, but you can definitely see it. It's not quite at the end line yet. It's got a little bit too far out here and a little bit too far in here, and you can see that it's just lagging behind the end line, which is this green one that stretches out and has a vertex about here, at about, I don't know, maybe 3.3 millimeters. But yeah, that's what this looks like. So now, that's pretty much it. That's all three of these, all of their contour maps, all their velocity maps, all their graphs, and that's the entirety of Project 1.